Hello everybody. Storage is a decentralized storage and compute platform, but let's focus on the storage part. In the storage part, anybody can run the storage nodes, which actually stores the encrypted and managed databases. And this software is recently updated to use a new storage backend, the hashstore. And hashstore is designed to be easy to use. Usually the storage node operators shouldn't configure anything, it just works. And the defaults are, I think, quite good for almost all of the cases. But if you are really interested about just adjusting the settings and tune the parameters, then I would like to explain the three most important configuration parameter in this video. So let's talk about hashstore first. So in hashstore, we have some metadata. It's kind of a database. In this particular storage node, it's in a SSD, so it's in a different directory. So here I have multiple directories. This is one satellite, and here I have the metadata, which is something like a database where we have the piece store, and we have a piece ID, and for each piece ID, which is the key, it points to a log file, which is somewhere here. And we have subdirectories just to make it easier to manage, and we have all the log files, usually 1 gig files. And the metadata directory, it just refers to one log file and it points to one segments like the beginning offset and the length. So let's execute this STBB helper just to check what is in the database part. We have some statistics, it points to 8 terabyte of data, which is nice. We have lots of entries like piece IDs and pointers to log files, but I can also check and compare the log files with the meta data part. I think I need the log directory and the meta directory. The meta directory is this one. Okay, and the log directory is storage storage node config storage hashstore. It will read both the metadata and the logs, and we'll create a report very soon. And this is the report, and you can see here the log files, the size. So probably I can just scroll up. So this is the log file name, this is the real size, and this is the bytes which are referred from the metadata. So these are quite good, right? All of them are referred and used. So these are almost full. We have a few specific log files which contains only TTL data, so they can be deleted once. But at the end of the list, we have some more problematic log files. So this log file, for example, is 1 gig, 1 gigabyte large, but only 0.83 gigabyte is referenced from the metadata. So all of the others are just dead. They are not trash, or because we need to keep the trash for a few days, but they are already expired trash or just deleted. So actually these bytes can be removed the log files. And this is what compaction can do. So before talking about the compaction, just be aware that we have two hash store here, you see that we have S0 and S0. I also have an S1. This is because we would like to use one of these during the compaction. So if we compact the S0, still during the time we can use the S1. And when somebody would like to download some pieces, then both S0 and S1 will be checked. So let's talk about the compaction. So one important thing is that it's the time of the compaction, it's not really configurable. There is some logic and it defines that the compaction will be happen with high probability once per day. And because we have two compaction actually, it means that once per 12 to hash store, it's once per half day. And if we were so unlucky that it didn't happen during the last 24 hours, then it will be triggered anyway. But it's a random day. This makes the network more resilient because it's not the same time when all of the storage nodes are compacting, but it's kind of random. And with compaction, what the software will do is just iterate over all of the log files and check that what can be rewritten to a new file without the overhead. Well, actually, the exact logic is slightly more complex. First, we need to rewrite the metadata. So it will check this metadata file and just process it, and all of the records which are expired, for example, because TTL or too old, they will be just removed. That's why we have these bytes which are not referred anymore. And after that, it will pick a few log files and rewrite. Not all of them, just a few, because we have limited free space. So we couldn't just rewrite all of these because we may have 4 terabytes of free space for this. I think the overall usage was 4.8. What about if we can free up, I don't know, 800 gigabyte? It means that we need way more free space. So this is limited, that how many log files can be rewritten. And that's why we have the first important configuration. This is rewrite multiple. The base is the size of the metadata, which is usually 16 gig or 8 gig, depends how big is your node, or 4 gig if it's a small node. So by default, it will rewrite only the hash store metadata and 10 times 17 gig, which is 170 gig of log files. But this is just one iteration. So when once in the 12 hours it will start to compact, it will iterate over and over and again and again. And during one iteration, it can rewrite only 170 gig with the default settings. If you would like to, if you have lots of free space and you can guarantee that the free space will be there, then you can increase this one. The next one, the fraction and the probability power. And this is way more tricky. Because here we can just calculate that, okay, what is the percentage of one log file? What is the percentage of the useful data in one log file? So this is the useful data, this is the size, so it's kind of 90%. And there is a probability for each of the log files to be picked for rewrite. And this probability is not very easy, but I have this simulator. So this is the probability, this is the 90%. And for each percent, I calculate the probability. And the most important part is the fraction from the configuration. This fraction, which is 0.25 by default. And the other one is the probability power. and which is used by here. The default is 2, probability 2, default 2. Okay, so let's use the defaults, and this is the percent of the useful data in the log file, and this is the probability of being selected in one iteration. So if there is only 10% of useful data in the log file, there is 900% to be selected. So it's 100% sure that they will be selected. Same is true for 20%. For 70% useful data, there is a very low chance, actually I think it's 2%, then it will be selected. So if you have 100 files with 70% of useful data, then 2 files will be selected in one iteration. And all of these will be processed. So first database and all of the hash table, the metadata, and all the files. And if everything is done, then the compaction will be finished. But usually that's not the case. So it will trigger a new compaction cycle at the same time. So it's once per half day. It will just do one iteration, do all the compaction, and next time it will check again all of these probabilities. So these will be zero with very high chance, because we had 100% that they are selected. So I think I think that compaction should rewrite all of those files. But here actually we had just 2%, so which means that 2 files out of the 100. So for next compaction, another 2 files will be picked up. And we are just going again and again until we have nothing in the selection. So there is very high chance that these will, or actually 100% chance that these will be selected. But because here we have a few percentage and we just select again and again, then these files will be processed in one of the compaction, and the compaction can be very long. So if we would like to decrease the chance that we process the less important part of the log files, then we should increase the probability factor, this one. So the probability power, if it's increased to 5, for example, you can see that there is 0 chance for these to be included, and it's very low chance. So it will focus only for these selected. So if you increase the probability, then these long tails will be removed, and probably the compaction will be faster in exchange that these files won't be compacted with a lower chance. Okay, if you increase the fraction to 0.7, then you can see that more log files will be compacted with 100% chance, and even for these we have pretty high chance. This is 1/3, so with each compaction 1/3 log files with 80% useful data will be compacted, and because at each iteration it can find new files, at least 3 iterations of the compaction will happen, and eventually only this file will remain. So probably it also useful to increase this one to 4, which means that we are interested about these files and not so interested about these files. This is 10%, so probably this will generate at least 10 compaction cycle and compact all of these, even if the chance is very low. But I think there is a good chance that some of these will remain. So if you have enough I/O capacity and you would like to store slightly less data in exchange of rewriting the same bytes again and again, which generates more I/O, you can bump this fraction. But if you would like to make it more predictable or less randomized, then you can increase the probability value. But in exchange, then these uh, won't be compacted. The reason why it's probability based and why it's not the reason why it's not very good idea to use a very high number is that if we do something like 5 here, then these won't be compacted ever with very low chance, right? So they will just they will be used, but the useful bytes will be decreased slowly, and at one point they will cross the threshold altogether, and the compaction should handle all of these files at the same time. That's why we need some randomization and some probability that, okay, always do the important files and some of the not so important files. Just it's an investment in the future, just to do it today, because we may have some spare capacity of the I/O. In that case, we don't need to do all the compaction all together. It's important that you need the free space for the compaction. Without free space, we couldn't. That's what we can adjust with the rewrite multiple. But because the termination condition also use this one, so we just select lots of log files what we can do, and if we couldn't select more log files, we will terminate, no more cycle. Then it there is an effect of this also on when we stop the compaction. At least that's the current implementation. It might be improved in the future based on the collected data and how does it work. And as I said, most of the time I think that defaults should be good enough, but this is how does it work under the hood. If you have any more questions, let me know in the comments or in the storage forum, and see you next time.